Properties of logs. Change of base. Log base b of a equals log base c of a divided by log base c of b. Proof. Let log base b of a equals x. Rewriting as an exponential gives b to the x power equals a. Taking the log base c of both sides of this equation gives log base c of b to the x power equals log base c of a. Now, utilizing the exponent property for logs on the left side, x multiplied by log base c of b equals log base c of a. Dividing, we obtain x equals log base c of a divided by log base c of b. Replacing our original expression for x, log base b of a equals log base c of a divided by log base c of b. With this change of base formula, we can finally find a good decimal approximation to our question from the beginning of the section. Example 10. Evaluate log base 2 of 10 using the change of base formula. According to the change of base formula, we can rewrite the log base 2 as a logarithm of any other base. Since our calculators can evaluate the natural log, we might choose to use the natural logarithm, which is the log base e. Log base 2 of 10 equals log base e of 10 divided by log base e of 2 equals natural log of 10 divided by natural log of 2. Using our calculators to evaluate this is approximately 3.3219. This finally allows us to answer our original question. The population of flies we discussed at the beginning of the section will take 3.32 weeks to grow to 500. Example 11. Evaluate log base 5 of 100 using the change of base formula. We can rewrite this expression using any other base. If our calculators are able to evaluate the common logarithm, we could rewrite using the common log, base 10. Log base 5 of 100 equals log base 10 of 100 divided by log base 10 of 5. So approximately 2 divided by 0.69897 equals 2.861. While we can solve the basic exponential equation 2 to the x power equals 10 by rewriting in logarithmic form and then using the change of base formula to evaluate the logarithm, the proof of the change of base formula illuminates an alternative approach to solving exponential equations. Solving exponential equations. 1. Isolate the exponential expressions when possible. 2. Take the logarithm of both sides. 3. Utilize the exponent property for logarithms to pull the variable out of the exponent. 4. Use algebra to solve for the variable. Example 12. Solve 2 to the x power equals 10 for x. Using this alternative approach, rather than rewrite this exponential into logarithmic form, we will take the logarithm of both sides of the equation. Since we often wish to evaluate the result to a decimal answer, we will usually utilize either the common log or natural log. For this example, we'll use the natural log. Natural log of 2 to the x power equals the natural log of 10. X multiplied by the natural log of 2 equals natural log of 10. X equals the natural log of 10 divided by the natural log of 2, which is approximately 3.3219. Notice that this result matches the result we found using the change of base formula. Example 13. In the first section, we predicted the population in billions of India t years after 2008 by using the function f of t equals 1.14 multiplied by 1 plus 0.0134 to the t power. If the population continues following this trend, when will the population reach 2 billion? We need to solve for time t so that f of t equals 2. T equals 1.14 multiplied by 1.0134 to the t power. 2 divided by 1.14 equals 1.0134 to the t power. Natural log of 2 divided by 1.14 equals the natural log of 1.0134 to the t power. Natural log of 2 divided by 1.14 equals t multiplied by the natural log of 1.0134. T t equals the natural log of 2 divided by 1.14 divided by natural log of 1.0134 is approximately 42.23 years. If this growth rate continues, the model predicts the population of India will reach 2 billion about 42 years after 2008 or approximately in the year 2050. Example 14. Solve 5 multiplied by 1.07 raised to the 3t power equals 2. To start, we want to isolate the exponential part of the expression, the 1.07 to the 3t power, so it is alone on one side of the equation. Then we can use the log to solve the equation. We can use any base log. This time, we'll use the common log. 5 multiplied by 1.07 raised to the 3t equals 2. Divide both sides by 5 to isolate the exponential. 1.07 raised to the 3t equals 2/5. Take the log of both sides. Log of 1.07 raised to the 3t equals the log of 2/5. Use the exponent property for logs. 3t multiplied by log of 1.07 equals log of 2/5. Divide by 3 multiplied by log 1.07 on both sides. 3t log of 1.07 divided by 3 log of 1.07 equals log of 2/5 divided by 3 log of 1.07. T equals log of 2/5 divided by 3 log 1.07, which is approximately negative 4.5143. Note that when entering the expression on your calculator, be sure to put parentheses around the whole denominator to ensure the proper order of operations. In addition to solving exponential equations, logarithmic expressions are common in many physical situations. Example 15. In chemistry, pH is a measure of the acidity or basicity of a liquid. The pH is related to the concentration of hydrogen ions, H+, measured in moles per liter by the equation pH equals negative log of H+. If a liquid has concentration of 0.0001 moles per liter, determine the pH. Determine the hydrogen ion concentration of a liquid with pH of 7. To answer the first equation, we evaluate the expression negative log of 0.0001. While we could use our calculators for this, we do not really need them here since we can use the inverse property of logs. Negative log of 0.0001 equals negative log of 10 to the negative 4th power equals negative multiplied by negative 4 equals 4. To answer the second question, we need to solve the equation 7 equals negative log of H+. Begin by isolating the logarithm on one side of the equation by multiplying both sides by negative 1. Negative 7 equals log of H+. Rewriting into exponential form yields the answer H+ equals 10 to the negative 7th power equals 0.00000001 moles per liter. Logarithms also provide us a mechanism for finding continuous growth models for exponential growth given 2 data points. Example 15. A population grows from 100 to 130 in 2 weeks. Find the continuous growth rate. Measuring t in weeks, we are looking for an equation P of t equals a multiplied by e raised to the rth power so that P of 0 equals 100 and P of 2 equals 130. Using the first pair of values, 100 equals a multiplied by e raised to the r multiplied by 0, so a equals 100. Using the second pair of values, 130 equals 100e raised to the r multiplied by 2 power, divide by 100. 130 divided by 100 equals e raised to the r multiplied by 2 power. The natural log of 1.3 equals natural log of e raised to the r multiplied by 2 power. Use the inverse property of logs. Natural log of 1.3 equals 2r. r equals the natural log of 1.3 divided by 2, which is approximately 0.1312. This population is growing at a continuous rate of 13.12% per week. In general, we can relate the standard form of an exponential with the continuous growth form by noting using k to represent the continuous growth rate to avoid the confusion of using r in two different ways in the same formula. A multiplied by 1 plus r raised to the x power equals a multiplied by e raised to the k multiplied by x power. 1 plus r raised to the x equals e raised to the k multiplied by x power. 1 plus r equals e raised to the k. Converting between periodic to continuous growth rate. In the equation, f of x equals a multiplied by 1 plus r raised to the x power, r is a periodic growth rate, the percent growth each time period, weekly growth, annual growth, etc. In the equation, f of x equals ae raised to the kx power, k is the continuous growth rate. You can convert between these using 1 plus r equals e to the k power. Remember that the continuous growth rate k represents the nominal growth rate before accounting for the effects of continuous compounding, while r represents the actual percent increase in one time unit, 1 week, 1 year, etc.